In this video, we pick up from our previous video where we were determining through the Kruskal-Wallis H-test if there was a statistically significant difference between the three groups in our study, and we found that there was a statistically significant difference, rejecting the null hypothesis. So the next step is to conduct the parametric equivalent of a post hoc procedure. Now that we've rejected the null hypothesis in the overall test, now we have to go through and determine which of those groups are different from each other in a pairwise manner. And if we have that a statistically significant H value, we then move on to the average ranks or the mean ranks of each sample. Now the line is a little bit obscured here, but this is the R with a bar on top of it. So this is the average rank, which is just simply the sum of the ranks for each group divided by the sample size of each group. And we see that here on the table on the bottom. So this is an excerpt of the table from the previous video where our summed ranks for group 1 is 27, 29, and 64 respectively for groups 2 and 3. Each had the same sample size, giving us an average ranking, as you can see, of 5.4, 5.8, and 12.8. And the next step is to determine how many pairwise comparisons that we need to make here. So we have this general formula where K, as illustrated in the previous video, represents the number of levels in our study, or in this case, the number of groups. We have 3 groups. So we just substitute the 3 for K in this equation, and we find that we have 3 pairwise comparisons to make. So we will compare group 1 to group 2, group 2 to group 3, and group 1 to group 3. And to do this statistically, what we need to calculate is something called a minimum significant difference. And this is the standard we're going to use to compare each group to each other in a pairwise manner. And the equation that we will use to determine that MSD, the minimum significant difference, as you can see right here. So on the left-hand side of this inequality symbol, we have the absolute value of any 2 groups in our study. This could be group 1 and group 2, group 1 and group 3, or group 2 and group 3. So the I and the J just represent placeholders, if you will, where we would substitute 2 different groups. Obviously, since we have I and J, this would not be the same group. So the absolute value of this difference, if this absolute value of this difference is greater than this quantity here, then we would determine that those 2 groups are statistically different from each other. And in this case, uppercase N represents the total number of participants collapsed across all 3 groups, where the lowercase n, as you can see here, represents the sample size in each of the 2 groups that we're comparing with the I and the J. And so this formula indicates to us that we can have different sample sizes in each group, and an equation like this will make an adjustment for those different sample sizes. But in our example here, that's not the case. So we would just substitute a 5 and a 5 for the 2 groups that we're going to compare. So the Kruskal-Wallis H-test, this post hoc procedure, is going to evaluate the absolute difference in any pairwise comparison, and if it exceeds the MSD, then we would determine that it is statistically significant. There is one variable in that equation on slide 50, and that's the Z value. And the Z value is based on the total number of comparisons that we will be making. And we already determined that on slide 49, where we had 3 pairwise comparisons that are to be made. And we also need to determine what's called the alpha level. So the type 1 overall family-wise level of risk that we are willing to take, and as to be consistent here, unless stated otherwise, we're just automatically go with 0.05. So we'll need to use this table here that will help us to determine the value of z that we will input into our equation that we were introduced to on slide 50. So uppercase N in our study will be a 15, the same N here, which is 15, and the lowercase n of any of the two groups, we had equal sample sizes, so this would be a 5 and a 5 regardless of the two groups that we put into here on the left hand side of this inequality. The only variable left to determine is the z, and we would use this table as you can see right here. So recall that we had our average ranks. Remember, we're comparing the ranks, not the raw data. So we had an average rank of 5.4, 5.8 for groups 1 and 2 respectively, and a much higher average ranking for group 3 at 12.8. So coming to the table, we first determine our alpha level, and unless stated otherwise, we always go with 0.05. And then in terms of the number of comparisons, once again, we have 3 comparisons, and we find the intersection of these two values, and we have our value, our z value. This is what we would input into this equation of 2.394. And we're going to do that here on this slide. So revisiting our equation, I inputted the value of 15, that's our total sample size, and now we fill in the rest of the equation where we have the sample size in any of the two groups. So I still have the I and j. Once again, this could be a 1 and a 2, a 1 and a 3, or a 2 and a 3. That's why we have these letter symbols in the subscripts. Regardless, it's going to be a 5 and a 5 because we have same sample sizes, and our z value is 2.394. And so running through the math here, we have a value, a minimum significant difference value of 4.28. So the next step is to calculate the absolute value of the difference in the average ranks among these three groups. So we took care of the right hand side, now we got to take care of the left hand side. So we typically set this up where we now compare group 1 and group 2. We just take the difference and take the absolute value. Because we're taking the absolute value, the order does not matter in which you put these values in. So if you end up with a negative value, you just take the absolute value of it. You don't keep the negative sign. So we substitute the averages of 5.4 and 5.8, and we set up the equation for the comparison between group 1 and group 3 and group 2 and group 3, and we just substitute the average ranks, calculating we have a difference of 0.4 between the average ranks of these two groups, 7.4 between group 1 and group 3, and 7.0 between group 2 and group 3. And so the 4.28 becomes our standard to compare these values against. So what we see right here, since 0.4 is not greater or equal to our minimum significant difference, we would conclude that these two groups are not statistically different. So this is statistically not significant. And that relates back to the fact that the pain ratings provided by those participants between the two different treatments were not statistically different from each other. However, when we compared the ice treatment and the massage treatment to the situation where there was no treatment, we see that there was a statistically significant difference between the two treatments and the no treatment condition. And what we would conclude here is that the application of a post-exercise treatment of ice bath or massage was superior at alleviating pain perceptions or pain symptoms following an exercise session than doing nothing. However, the advantage of one treatment over the other, the ice bath versus the massage, was not more advantageous than the others because they were found to be statistically not significant. So this ends this video on the Kruskal-Wallis H test.